In this video, I'll demonstrate how a number of Heathkit computer products are able to run in emulation on a desktop computer using the MAME emulator software. MAME, originally standing for Multiple Arcade Machine Emulator, is open source software designed to recreate the hardware of arcade game systems and software on modern personal computers. It does this by emulating the inner workings of the hardware, including the processor, in software and running the original ROM or cartridge code. The project has been active since 1997 and now supports several thousand different systems. MES, an emulator for video game consoles and computer systems based on the MAME core, was integrated into MAME in 2015. See the mamedev.org website for more details on the project. In this video, I'll focus on MAME support for some Heathkit computer products. Note that this video was recorded in January of 2024 and was based on the version of MAME from GitHub at that time. As MAME is under active development, some features and details may change in the future. I'm running it here under Ubuntu Linux. MAME is also supported on Windows and Mac OS. Heathkit and its parent company over much of its history, Zenith Data Systems, made a number of computer systems in the 1970s through 1980s. The following Heathkit models are supported by MAME: the ET3400 microprocessor trainer, the H8 digital computer, the H19 video terminal, and the H88 and H89 computers. I'll demonstrate each of these in the video. Supported Zenith models include the following: the Z22, Z29, and Z150 video terminals, and the IBM-compatible Z100, Z150, Z160, Z180, Z248, and SuperSport computers. I won't cover these as they're of less interest to me personally and I haven't tried them. Installing, configuring, and running MAME in general is covered by the MAME documentation on their website. On Linux distributions such as Ubuntu, MAME should be available as a package. If you want to run the very latest development version, you can check the source code out of the project's GitHub repository and build it yourself. This initially takes some time as it's quite large. For the demos here, this is what I've done. Most MAME platforms, including the Heathkit ones, require obtaining product ROMs. These are not included with MAME as they may be protected under copyright. Depending on the product and the laws in the country where you live, the device ROM code may or may not still be under copyright. If you own a real system and have suitable tools like a ROM programmer, you could extract the ROM data, or you may be able to find the files on the internet. MAME expects the ROM files to be in binary format and packaged in a zip archive with files having specific names. MAME will tell you if they're missing or have the wrong checksums. For emulators of systems that are disk-based, you'll also need disk images for the operating system and applications. They can also be found on the internet, and in some cases, like for Heathkit's HDOS, the code has been explicitly released to the public domain. I'll say a little more about disk formats when I demonstrate specific systems, but I won't get into a lot of detail in this video. Let's move on to the first demo. The Heathkit ET3400 was a microprocessor trainer designed to teach hardware and software for the Motorola 6800 microprocessor. Introduced in 1976, it was one of several trainers offered by Heathkit. It was very popular and Heathkit sold many of them. I own a real ET3400 and have made a separate YouTube video on it. In short, it was a self-contained Motorola 6800-based single-board computer with RAM, ROM, 7-segment LED display, and keypad. An optional ETA 3400 expander board provided more RAM, additional ROM and containing a tiny BASIC interpreter, a serial port, and a cassette tape interface for mass storage. Here is the MAME emulator for the ET3400 running in full screen mode on a Linux-based laptop. It emulates the 7-segment LED display as well as the keypad. You can click on the keypad or type keyboard keys to activate them. The ET3400 monitor allows you to enter and run programs including setting and displaying CPU registers, setting breakpoints, and single-stepping through code. For example, I can examine memory address 1000, change the value to AA, move to the next location, or move back and see the value of AA is still there. And I can see the various registers like accumulator A, accumulator B, and the program counter. It also emulates the ETA 3400 expander's serial interface by executing the code at address D1400 by doing do 1400. We start up the serial monitor program, which provides a command line interface. A typical monitor command is this one to dump a block of memory in hexadecimal. We can execute the tiny basic interpreter that's in ROM by executing the code at address 1C00. I can now enter and run a simple basic program. The ETA 3400 had a cassette tape interface for saving and loading programs, and this is also emulated by MAME. It works from the serial monitor as well as from Tiny Basic. You need to configure MAME to associate a file with the cassette tape. There are also controls provided in MAME to operate the simulated cassette tape. We can save the program from BASIC using the save command, and MAME writes the sound as a WAV file to disk. Then we can later load the program back from tape. I'll demonstrate loading a program I saved earlier. First, let's delete the current program from memory. And then run the load command. The MAME shortcut key F2 will start the simulated tape in play mode. You can hear the audio on the laptop when it's playing. After about 45 seconds, the basic prompt returns and the program is loaded. If you had an old cassette tape with data from a real ET3400 system, you could transfer it to a PC as a sound file, and MAME could load the data from the tape into the emulated ET3400. The next device to demo is the Heathkit H19. This was a serial terminal and was intended to be used with computers like the Heathkit H8 or H11 or any computer supporting an RS-232 interface. Introduced in 1980, it was an improvement over the earlier H9 model, which was quite limited in functionality, only displaying uppercase characters, for example. Firing it up, you can see that MAME closely replicates the character font and color. In fact, it's running the actual firmware of the real H19 on a simulated Z80 processor. Note that there were several different variants of firmware available for the H19, and MAME supports several of them. Opening the settings allows you to set options, or what MAME calls dip switches. Other settings are under machine configuration. By default, the terminal is in loopback mode and simply echoes back what's typed. Like other MAME-based terminals, you configure it to connect to different ports. By selecting to use a sudo TTY under Linux, you can connect it via a program like SOCAT to a program or even a real serial port on a desktop computer and use it as a real terminal. We'll talk more about the H19 when I demo the H88 and H89 computers. The H8, along with the H11, was one of the two first digital computers introduced by Heathkit in 1977. It featured an Intel 8080A processor running at 2.048 MHz, 4K of ROM and up to 32K of RAM, a beeper, a serial port, and a cassette tape interface. It initially sold for US $379 in kit form. To be useful, you also needed a serial terminal like the Heathkit H9 or H19 and a cassette tape recorder. They later offered the H17 floppy disk controller that supported up to 3 floppy drives. With that, it could run the CP/M operating system or Heathkit's proprietary HDOS. More on that later. Later, they offered a more powerful Z80-based CPU card. The H8 had a front panel that provided 9 7-segment LEDs, 4 status LEDs, and a 16-key keypad. This allowed entering, running, and debugging programs and loading and saving to cassette tape. While it looks primitive, it was actually an improvement over other computers of the time that used toggle switches to manually enter programs as binary 1s and 0s. Firing up the MAME H8 emulator, we can see the display. The front panel keys are not shown in the GUI and are mapped to keyboard keys. This diagram shows how the keys were laid out along with the MAME keys in parentheses where they differ from the key labels. Note that the H8 front panel uses octal, base 8, and not the more common hexadecimal, base 16, representation for addresses and data. This was the convention in the early days of programming the Intel 8080. Addresses are 6 octal digits up to 177777, and data is 3 digits, 000 through 377. The later Z80 upgrade allowed hexadecimal entry with new keypad labels. The operation manual for the H8 covers how to use the front panel, as well as the manual H8 computer front panel monitor PAM8. The first manual has an initial test program, as well as memory test routines that can be entered and run from the front panel. Let's try entering and running the official test program from pages 4 to 8 of the operator's manual. It's somewhat tedious to enter, but I can use MAME's paste feature to directly paste the data into the emulated machine. As expected for a working machine, it displays your H8 is up and running and then beeps. It's possible to save and load programs to simulated cassette tape. You use the dump and load routine supported from the front panel. As with the ET3400 shown earlier, you configure the tape device and file in MAME. Earlier, I entered and saved a memory test program from the H8 manual. Let's try loading it from tape by pressing the 8 or load key and then F2 to instruct MAME to start playing the tape. If successful, it counts to 377 on the left 3 digits and then repeats. On a memory test failure, it stops on error. It looks good here so far. Heathkit provided a number of programs for the H8 on cassette tape or on perforated paper tape, which was supported by the H10 paper tape reader and punch. The programs included an 8080 assembler as well as the Benton Harbor BASIC interpreter. On a real H8, it was possible to add a floppy disk controller and drive and boot from disk. The MAME H8 emulator allows selecting floppy disk controller BIOS ROMs, but I don't see any way to use this currently as there is no disk controller or serial terminal support. If you want to run in a disk operating system, then the H89 is probably a better option. We'll look at it shortly. Now let's look at the H88 and H89 computers, starting with the H88. The functionality of the H19 terminal and H8 computer were combined into the Heathkit H88 and H89 computers. In fact, it was possible to upgrade an H19 to an H88 or H89 computer. The MAME H88 and H89 emulators make use of the H19 terminal emulator we saw earlier. The H88 model was a version with CPU, a Z80, and screen, the same control board as an H19 terminal, and offering a cassette tape interface for mass storage. It had no front panel like the H8, but instead had a simple command line monitor accessible from the screen and keyboard. When powered up, you're presented with a simple serial monitor that provides functions for entering and running programs, including breakpoints, and saving and loading from cassette tape. Like the H8, it uses the octal numbering system, but in this case it used what was known as split octal, where addresses are 6 octal digits ranging from 000000 to 377377. Data bytes range from 000 to 377. For a demo, I'll use an example program that was outlined in the H88 monitor manual. When run, it waits for the user to enter an octal number followed by enter. It then uses the system's clock interrupt to count down and display the specified number of seconds, and then display a beep and return to the monitor when done. As before, I can paste the program in from a text file I've previously prepared to avoid manually typing it in each time. The start address is 40100. Let's enter 10 or 8 in octal and press enter. As with the H8, there is support for cassette tape storage, in this case using monitor commands. Here I can load a previously saved version of the same program using the monitor L command. The emulator in this case is smart enough to start tape playback automatically. As with the H8, you could obtain programs from Heathkit on cassette tape or paper tape and load and run them in this way. By today's standards, this was very slow and tedious. Even at the time, users that could afford it would have likely upgraded their H88 to add a floppy disk controller and disk drives. As mentioned, the H88 could be expanded to add external floppy drives. The H89 was a more expensive model that included built-in floppy disk support rather than cassette tape. Most users of this machine would have run a disk operating system, either CP/M or Heathkit's HDOS. Currently, MAME only supports the Heathkit H8938 soft sector disk controller. A hard sectored controller was more common, but it's not yet supported. These were 5 1/4 inch floppies, typically storing just over 100 kilobytes per disk. The controller supported up to 3 disk drives. You can find suitable disk images that will work with MAME on several Heathkit sites. There are also tools that allow you to manipulate images from a Linux system. I may cover more details on this in a future YouTube video. One of the operating system options was CP/M. This became an industry standard for 8080 and Z80 based systems before it was supplanted by the IBM PC and MS-DOS. Programs written for CP/M were generally compatible across other CP/M systems, of which there were many manufacturers. Heathkit offered several releases of CP/M, the latest being 2.0.04, and at least one third party offered CP/M 3.0. Here's a demo of booting up CP/M on the H89 emulator. From the console, we type B for boot. Note the realistic disk sounds that MAME makes when accessing the disk. I have 3 drives mounted and can access all 3 as drives A, B, and C. CP/M included some basic development tools like an assembler and text editor. Heathkit offered additional software from them, from third parties, and the Heathkit users group. Here's an example of building and running a simple assembly language Hello World program. I earlier created the source file hello.asm. We can assemble it. And now link it. And now run the program. Another operating system option for the H89 was HDOS, a proprietary OS written by them. Somewhat CP/M-like, it was written by Gordon Letwin, who later went to Microsoft to head their development of the OS/2 operating system. You can find the full Heathkit manuals for HDOS online. You can even find source code for it, as it was made open source in the 1980s. I may cover HDOS in more detail in a future video, but here's a quick demo. First, booting it. There's an obvious Y2K issue here, as you can't enter years past 99. There is a patch available to fix this. The dir command lists the disk directory. Other disks need to be mounted first before you can use them. A few more commands. Here's an example of running Heathkit's Benton Harbor Basic under HDOS. Let's enter and run a small program. I'll hit Control-C to stop it before it completes. You leave BASIC using the buy command. Before powering down the H89, you're supposed to shut the HDOS system down cleanly. Commands to do this are buy, quit, or halt. That final message is presumably a humorous reference to the famous Colossal Cave text adventure game. I don't know if the message was in the official HDOS release or added when it was made open source. I haven't learned too much about HDOS yet. It seems more comprehensive and powerful than CP/M, although more complex. The reference manual is over 700 pages long. And now some late-breaking news. I've been working away for some time on a new book project, this time a book about Heathkit computers. It's now complete and has been released for publication. Titled Classic Heathkit Computers, Calculators, and Robots, it aims to be the definitive guide to Heathkit computers. From the analog computers of the 1950s to the IBM PC compatibles of the 1990s. It includes coverage of the calculators, the Hero line of robots, microprocessor trainers and peripherals, as well as software and tips on restoration and repair. It sells for about US $25 and is available from lulu.com and soon from other retailers like Amazon. I hope you enjoyed this demonstration of some Heathkit computers running under the MAME emulator. Most of these computers are now quite rare and sought after, and this is a way to experience using them at no cost. In future videos, I plan to look at some of MAME's other retro computers. I may also do a deeper dive into running MAME on some specific Heathkit machines such as the H89 and HDOS. Thanks go to Mark Garlanger, who developed and maintains the H19, H8, and H88 and H89 MAME emulators. He's currently working on adding H89 hard sector disk support, which will make it usable with much more of the available disk images. His website, heathkit.garlanger.com, has a huge collection of information on Heathkit computers. From using MAME, I can foresee some interesting project possibilities. For example, a cool project could be to build a replica of a Heathkit H8 using MAME running on a small computer like a Raspberry Pi, with a hardware front panel with LEDs and keypad.